First, now that I'm getting more questions on homework, and a couple people have turned it in. Something I want to point out based on my experience from reading this assignment in the past. Now, if anyone has already turned it in because of oops moment because of this, that's fine. You can update your submission because as I mentioned, I don't really enforce due dates, and I'm not going to be looking at the assignments until like the end of the week, the weekend. Anyway, okay. Okay.
I just reach.
Now, this is one I've got questions about, because I'm deliberately vague about, you see how some behaves on a matrix, and then go to get the opposite behavior. I will accept any reasonable interpretation of what is meant by opposite behavior. Okay. This one about the Hilbert matrix. Please pay attention to every part of the question. I'm sorry if my homework problem statements are annoying due to having multiple parts. What's happened in the past is a number of people have blown off this part right here. And if you at least show an effort towards that, but that's worth something. Don't blow off parts of the question. Okay, this one, you have to produce two functions. So what I want is two .m files, one for each function.
Two .m files.
Yeah, one for sine, one for cosine that handle the angle in degrees. Now the functions you're implementing that compute sine and cosine with an angle in degrees, they already exist in MATLAB. They're called sine d and cosine d, but you're implementing your own. So you should call them something else. Also, these functions should the only thing they do is compute the sine or the cosine, and then they return that value as an output. There's no interaction with the user in terms of input or output, like nothing asked for, nothing prompt user for, nothing printed. It's meant to be a black box. Think of it that way. So what happens is, like, if I'm running a MATLAB program that ought to have some kind of user interface that might prompt user things or print things, then like generally your top level code is going to handle that, and then your code is calling functions like these to carry out the actual computational tasks. Because when you're writing computational teams like these, you have no way of knowing how they're going to be used or what the user is going to do with the output that you furnish them with. That's their problem. You just handle the computation and get out. Okay. All right, that's all the comments I have about homework right now. But I should have some time at the end of class to address any questions of the assignment after I cover today's material. So last time I talked about error analysis, forward error, backward error, and so forth. And today I'm going to talk about convergence. But before I do that, as a follow-up to topic from last time, I'm going to do a MATLAB demonstration. Now, diary for this. Today is 12.
Diary.
Yeah, this is going to be a demonstration of one of the concepts we covered last time, the condition number. Now, the condition number is a ratio of forward error to backward error. So it's a measure of how error in the input is amplified to cause error in the output. Or what if you change the input by a little bit? If the condition number is large, that could change the output by a lot. So something you need to be careful about. So what I'm going to do is I'm going to fill in enter a 2x2 matrix, not just an arbitrary one, it's one I decide.
Saves automatically.
Dr. Lynn?
Yes.
My, this is normal, I just wanted to bring it up. But my MATLAB like takes a really long time to load
Oh.
in. Like when you open yours, it just like pops up the like command window and has these things, the signs. But mine like takes a while to load until it finally loads that and loads my my files and stuff.
Oh.
It takes like a good minute. I just don't know why.
Why does that also?
Yeah.
Well, I think one of the reasons why I got a faster computer because I got tired of MATLAB taking so much stuff and do things. Or just computation itself. I can't say I'm totally surprised. But I guess if your computer is generally fast at other things. Now, MATLAB is interesting piece of software and it has a combination of several languages. Like the lowest level functionality, like matrix operations, matrix multiplication, are implemented in Fortran, which makes sense because Fortran is the most efficient language. It's the oldest language ever, programming language, but it's still the fastest one, computation. Then MATLAB has its own interpretive language, but the user interface, which creates all these windows and so forth, I believe that's implemented in Java. So if the slowness is limited to that, it makes you wonder if something else with your Java installation. Because there's so many different versions of a Java virtual machine and so forth, and it might be a good idea. I'm not sure if MATLAB has its own self-contained Java engine or if it's using whatever's already on your system. And Java is something I tend to avoid dealing with at all costs, but we're kind of stuck with it. And all the annoying people who think that Java is good for everything, which is just ridiculous. So the only thing I can think of is if you go to, I think you just probably java.com or something like that just to make sure you're using like, the most up-to-date Java.
Thank you.
Okay. And so, okay, so here we have this 2x2 matrix. And now, for matrices, for square matrices, there actually is a formula for the condition number. It's not something I can really get into here because it's really a topic for the next course, 461. But there's a MATLAB function that implemented, so con, so for condition number of A. So for this matrix, it's a bit large. So,
That's not how mine turned out.
are you sure?
A. It's not how my A turned
Maybe something was typed wrong.
Or you have the format short.
Oh yeah, I have format long. So that's the only difference. So the condition number of this matrix is like 34,000 something. So what that means is, if you're solving a system of equations with this matrix, so AX equals B with this A change in B could lead to that change being amplified by this much, by like 34,000-ish in the solution X. Now it sounds kind of far-fetched, But here's what I'm doing. I'm going to input two choices for a vector b. So first one is 5, 2.6239, hopefully it's right. And then the other one is 3, 317. All right. So if I look at these vectors side by side, b1 and b2. All right. So here's b1, on the left, b2 on the right. They don't seem to be terribly different from one another. So you would think that if I solve ax1 equals b1, ax2 equals b2, so I solve ax equals b with both of these right-hand sides, then my solution should not be very different. So let's find out. Well, actually, first of all, I'll do is I'm going to check the relative difference between these two. So norm is a measure of magnitude of a vector or matrix. So if I look at b1, norm of b1 minus b2 over the norm of b1, that gives me a measure of how different b1 and b2 are, like a percentage difference. And in fact, it's roughly 1%. So these vectors are not very different at all. So now, to solve, I'm going to solve a times x1 is equal to b1. So to do that, I use the backslash. x1 is equal to a backslash b1. Okay, there's my solution. Nothing remarkable about that. Now solve the other system. A x2 is equal to b2. So same thing, a backslash, but now it's b2. So b1 and b2 differ by just 1%, but x1 and x2 differ by a ton. So instead of having like 1.1 and 0.1, here I have 213 and 273 minus 273. It's way off. So in fact, if I look at the difference between these two solutions, so they differ by 300%. So a 1% error got amplified about 30,000 times. And I said the condition number was like around 34,000. So theoretically, a change in B could be amplified by that much. And in this case, that's exactly what happened. Full disclosure, I contrived to make this happen. But the point is, if you're solving a system of equations with who knows what right-hand side, in some cases there can be many of them in some applications, then this is the risk. Even if the error isn't thrown off by the maximum possible amount, the solution could still be thrown off by a lot to an unacceptable degree. So this is an example of if you okay.
See, I got it, have it in front of me.
Yeah. So that you can't assume that a small change in the input to your problem is going to lead to a small change in the output. And we like well-conditioned problems like that, but we don't always have them. And even a problem that seems relatively simple, solving a 2x2 system of equations, can be problematic. All right, so any questions about this demonstration here?
When I did it, for some reason, once I started solving x2 and down, it's like the same number, but the decimal is 100th place messed up. So instead of like
Oh.
2.7, it's 272.
Oh, wait. So okay. Now, you sure everything gets typed in as is for A and B1 and B2?
Well, I assume it can't be.
Okay.
Something has to be messed up in there. But it looks like it's right. See later.
Well, this example is also in the book too. It's this example right here.
Okay. Thank you.
Yeah, so actually, here, this example illustrates conditioning. The example right below it, which I brought up last time, illustrates stability. That this matrix right here is well conditioned, but if you use an unstable algorithm, Gauss elimination without row interchanges, then that doesn't go so well. Okay. Now, okay, these are the same notes from last time, but I only did the first half of them or so. Now I'm going to do the other half today to complete this section. That's going to take us down here. Convergence. So a lot of numerical methods are iterative in nature. We're going to see that at the end of the semester for solving nonlinear equations. All the methods that we see are iterative. They'll generate a sequence of approximations to the exact solution that hopefully will converge to the exact solution. Now, in a theoretical math class, like real analysis, convergence is an important topic as well, but generally focuses on whether something converges. In numerical methods, efficiency is also very important. We care about how rapidly sequence converges once we establish that it converges at all. So that's what leads to this notation, big O notation. So this is used to quantify how rapidly a sequence converges to a limit, or how rapidly a function converges to a certain value. So what is big O notation? So at first we're going to look at sequences. So we have some sequence a sub n that converges to some limit and then goes to infinity. So we say that sequence an is equal to big O of some other sequence bn if this relationship holds, that the absolute value of an is less than or equal to some constant times bn. And generally, the sequence bn ought to have a much simpler definition than that of an, because it's how we describe how rapidly it converges. So here's an example of applying big O notation. Okay. So here's my original sequence. So an is 3 plus 2n plus 5n squared. Now, I only need this relationship to hold for the index n sufficiently large. Now, if I take the absolute value of this, then I have this relationship because the first and last term are always positive, and then at the absolute value of this term. But suppose if n is greater than or equal to 1, and we here care about n being natural numbers, then I can make this simplification. I can say an is less than or equal to, I can use the highest power of n throughout, because if n is greater than or equal to 1, then n is less than or equal to n squared. So what I've done here is I've made every term the coefficient times n squared. I'm allowed to do anything to the expression that makes it bigger, because I'm looking for an upper bound. There's something you can teach about more in different classes, maybe earlier classes like discrete or something. Well, there's something that comes up a lot here, finding an upper bound for something. And what kind of algebraic manipulations you can make to get an upper bound. So now I can simplify this because I have all like terms. So I can say that if n is greater or equal to 1, then an is less than or equal to 10n squared. So now what that means is I can say that an is big O of n squared, because I have this kind of relationship. An is less than or equal to a constant c times n squared, where the constant capital C in this case is 10. Generally we don't care too much about what the constant is, just that there is one. So in general, you can show that if you have a polynomial, any polynomial of n is big O of n to whatever the degree is. So any quadratic polynomial is order n squared, any cubic polynomial is order n cubed, big O of n cubed, etc. So I slipped there, I said order. So that's another way of saying it. Like an is big O of bn, or it's order of bn. It's talking about like order of magnitude. The questions in this example about how we show that this sequence is big O of n squared. So you can think of it as capturing the most significant part of a function or sequence in terms of growth rate. So, big O notation can be used to describe what's called graded convergence. So suppose we have a sequence and we know it has a limit. So an converges to a. So then, if an minus a, so the difference between the sequence and its limit is big O of bn, then we say that big O of bn is the graded convergence of an to a. So here's an example. Here's my sequence. And I can show by techniques taught in calculus, like L'Hopital's rule, for instance, that the limit of a sequence, as n goes to infinity, is 2. So now what I'm going to do is I'm going to look at the difference between sequence and its limit. So what I have down here, I need to label this. This is an minus 2. So sequence minus its limit. Okay, here I filled in what the sequence is. And then here I've taken, I want to put everything over a common denominator. So this fraction here is just equal to 2. It's just written in such a way that we have a common denominator. So then I work out what all this is, and this is what I get. Now, I want an upper bound for this expression that's as simple as possible. And it just occurred to me that the kind of manipulations I'm doing here are also useful in class like real analysis. Those of you who are taking it or suffering through it. So if I do something that makes the numerator bigger or the denominator smaller, that makes the fraction as a whole larger. So what I do in this case, I'm taking absolute value. So here I have n plus 1. Well, if I replace the n plus 1 with n, that's upper bound. So, so I can conclude that an minus its limit of 2 is less than or equal to 2 over n squared. In other words, the rate of convergence is n to the minus 2. So if you have a sequence, a convergent sequence, that the rate of convergence is big O of n to the minus 1 versus another that's n to the minus 2, the latter sequence with the n to the minus 2 convergence rate is going to converge to its limit a whole lot faster than the other one. So the so as a guideline, the exponent that is closest to 0, in other words, the least negative in this case, that determines the rate of convergence. So like if you have an expression like 1 over n plus 2 over n squared plus 1 over n cubed, the most significant term is the 1 over n. That would be the rate of convergence. The other terms are less significant. Questions about this example? Okay, now that's about sequences. An as n goes to infinity. It's also worthwhile to look at rate of convergence of continuous functions, like a function f of h, as h goes to 0. An example of such a function might be a difference quotient that defines a derivative. You have f of x plus h minus f of x over h. As h goes to 0, that converges to a derivative. But at what rate? So we have a similar definition of big O notation for this. We still have this upper bound. So if we have a function f of h that's less than or equal to some constant times g of h, but now, instead of the case of n goes to infinity, and we care about n sufficiently large, we're dealing with h going to 0, and we care about h sufficiently small. Formally, you can think of h as corresponding to like 1 over n. So then we say that fh is big O of g of h. We have a similar definition for rate of convergence. So if f of h converges to some value f naught, as h goes to 0, then the rate of convergence is big O of g of h if the difference between the function and its limit is big O of g of h. Here's an example of that. Here we have this function, sine h minus h over h. So you can determine that as h goes to 0, that this fraction converges to 0. Because if I just plug in h equals 0, I'm going to get 0 over 0. But you use techniques like L'Hopital's rule, etc., to find out that the limit is 0. So to figure out the rate of convergence of this function to 0, use a Taylor polynomial for sine of h. So the beginning of a Taylor expansion, of a Maclaurin expansion of sine is this, so h minus h cubed over 6, and then this term is the Taylor remainder. So where's the Greek letter c, or squiggly, as I refer to it, is a unknown number between 0 and h. So I go ahead, just in general, here's your general Taylor's theorem that I applied here. n equal to 3. So what I do is I take this Taylor expansion and I substitute it for sine h in here, and then simplify as much as I can. And once I carry all the algebra from substituting this in here, a bunch of things cancel, and I'm left with minus h squared over 6, and then I have this term that comes from the Taylor remainder. But again, the exponent of h closest to 0, so the least positive exponent of h, is the one that determines the rate of convergence. So we say that, so this is the dominant term, because this is going to 0 a whole lot faster than this will be. So the rate of convergence is big O of h squared. So it doesn't matter whether we're talking about sequences as n goes to infinity, or functions f of h as h goes to 0. The exponent closest to 0 is the one that determines the rate of convergence. So in the case of sequences, you have negative exponents. When it's a function f of h, it's positive exponent. Either way, closest to 0. Questions about this one? Sorry for digging up any Cal-free trauma by mentioning Taylor series. One of my professors from undergrad actually referred to Taylor's theorem, which indicates what Taylor series is. Taylor expansion is as the fundamental theorem of numerical analysis. So it may be unofficial, but it's true. Yeah. Oh yeah, you especially was really good there. Okay. So here's another example of convergence function f of h. Here we have. Yes.
Please, I have a question.
Yeah.
From the f of h up there, which equals to sine h minus h. So after finding the Taylor polynomial and substituting it back to the sine h, what happens to the negative h?
Oh, so what happened was, okay, once this got, well, okay, actually, hold on, I'll go ahead and show it. Okay, so if I take this original fraction, and then replace the sine h by the Taylor expansion. Okay. Okay, so what you can see here is the h as leading term in Taylor expansion cancels with the h over here. And then everything that's left, we have h cubed, we have h to the fourth, but we're dividing by h. And that's what leads to the h squared here and the h cubed here. So it's generally what happens when you substitute Taylor expansion, you get a big old cancellation test. Now, As another example, you're familiar with the difference coefficient for a derivative, f of x naught plus h minus f of x naught over h. Here we have one for the second derivative, which amounts to applying a first order difference coefficient twice. So as h goes to 0, this expression right here converges to the second derivative. For now, you can take my word for it, but when we get to chapter 9 later in the semester, you'll see how approximations of a derivative like this are derived. But what we want to look at here is, okay, if this converges to the second derivative, as h goes to 0, how rapidly does it do so? So for that, we again use Taylor expansions. But we need two of them, one for f of x naught plus h, and then for f of x naught minus h. Taylor expansion centered at x naught. And that's what we have here. Here are those two Taylor expansions. And you'll see that they're very similar. It's just that to get the second one from the first one, you replace h by minus h throughout. And this is what you get. But I want to emphasize with Taylor's theorem, the remainder is evaluated at an unknown point between the center and the point you're evaluating at. So C1 is some unknown value between x naught and x naught plus h. Here too, in the second expansion, you have an unknown value, but it's between x naught and x naught minus h. So these two are different. I want to keep that in mind for later. So, like in the previous example, I'm going to take these two Taylor expansions and substitute them into this fraction right here. Notice we have f of x naught plus h here and plus f of x naught minus h here. So these get added together. Well, that means that these terms, f of x f prime of x naught h, those are going to cancel. These terms are going to cancel. These terms are going to add together. And then here we have these terms, these two will also add together. There's 2f of x naught. But then we have minus 2f of x naught here, that's going to cancel them. So, a whole bunch of things will cancel. And what ends up being left is what I said this would converge to, f double prime of x naught. But then, the next terms that don't cancel are these right here. These terms involving the h to the fourth. But everything is divided by h squared here. So now we have, so now I have this. Oh, what do we have this blank space? Oh, okay, I need to get rid of that. Hold on. Oh, okay. I have a new page command in here. I don't want that. Okay. Now, so I'm going to simplify this using something that you learned about in Calculus 1 and made very little use of probably. This is what happens in higher level math classes. We think of concepts that you see in lower level math classes long after you've had the opportunity to forget them and use them in entirely different ways. And that is what makes making that hard. That's our dirty secret. Okay, so the intermediate value theorem. Okay, so a function is continuous on interval, then f assumes every value between f of a and f of b, values of the endpoints. somewhere in the interval. Now, in the calculus class, they probably give you some really stupid problem that goes with this, like, oh, okay, f assumes every value in between, so find out what the value is. Intermediate value theorem is an existence theorem. So I don't know why they did that, but anyhow. So if a function is continuous, so here we're going to assume that the fourth derivative of f is continuous. All right, so if f assumes every value between f of a and f of b, that would include the average, because the average of these two is going to be a value between f of a and f of b. So what I've done here, I have h squared over 24, but notice I've broken it up. I have h squared over 12, and then I have 1/2. And that seems kind of odd, but here's why I wrote it that way. What I have here, 1/2 times this expression in square brackets, is the average of these two values. So, if I assume that the fourth derivative is continuous, then there has to be some unknown point, I don't know where it is, I don't actually care where it is, between x(1) and x(2), such that the fourth derivative is equal to this average value. Now, x(1) is between x0 and x0 plus h. c2 is between x0 minus h and x0. So both of these together are in between these 2 points. And this average is also there. So I can replace this average with fourth derivative at some other unknown point that's between these two. Now it's called plain old squiggly. So now my error term, if you will, has simplified to this. So that's why I went through this whole intermediate value theorem rigmarole, to get the simplest expression possible for the difference between this expression, this function of h, and what it's converging to, at double prime of x0. So I can conclude that this formula for approximating f double prime of x0 is big O of h squared. So that's the rate at which the approximation is converging to the exact value. What that would mean is, if I reduce h by a factor of 10, then the error in my approximation would reduce by a factor of 100. And certainly, higher order expressions like these are preferable to lower order ones. Okay, that was a mouthful. Is there any questions about what happened here?
Did we need to write the notes down?
Oh, no, that's what I do it right. You can look at these later. And then, of course, all this that we see here is based on the book. I actually got to know in the first place by trimming down what was in the book. And then you look there for more information. They come to the end of the notes. Wow, I have. And here I have the mean value theorem stated for no reason. I guess when I last used these notes in 2021, the last time I taught this class, I felt some compelling reason to put this in here. Mean value theorem actually is a very useful theorem in numerical analysis. And this is, okay. Although it's closely related to the mean value theorem for integrals, and it's close relative to a weighted mean value theorem for integrals, which is actually what's used to derive the Taylor remainder. Okay. That's not something I made to see. Okay. And I'm sure that this is going to rear its ugly head later. One of the homework problems forms from this section deals with various approximations, specifics of a first derivative. So Taylor expansion is going to come up some of the whole problems. Okay. Well, but yeah, that concludes this section, 2.1. The next couple classes are dealing with the remainder of chapter 2, 2.2, but it's about the computer arithmetic, rounding error. So I guess now I have way too much time for questions about anything such as homework. I see a whole bunch of sparkling 100 homeworks.
The 1.2.26.
26. Okay, hold on.
How about finding the formula?
Okay.
What? Oh, the matrix.
Yeah.
Okay, so about this problem.
But what about the notes for but what about the notes in MATLAB for today?
Oh, I'm gonna post those.
So can we just do diary off now?
Yes. Yeah, I don't think I'll be doing any more about it today. It depends on what people ask. Oh wait. Okay. Okay.
Diary off.
Well, yeah. Okay. That's a demonstration. But anything else I do will show up in the video. Okay. So I look at Hild 5. Oops, the generation 5x5 Hilbert matrix, but this is not a very helpful format. I do format RAT for rational.
Format rat,
And that will
not format rat.
okay. So it is since this format has a simplest expressions for matrix entries. Okay. What is, if I refer to this matrix as H, what is H I J in terms of I and J? And it might be helpful, it would be helpful to consider examples for I and J.
I'm sorry, Hill what?
Oh, whoops. That is what is Hij in terms of I and J. So, for example, if I let I equal to 1, and then if I look at the first row, so then J is equal to 1, 2, 3, 4, 5. Then if you use that to figure out the entries of a first row as a function of J, and then do the same for the second row, then you can start, it's basically extrapolating from patterns.
I have a question.
Yes.
So, I wrote down that formula, the expression as a comment.
Okay.
And is it alright if I, like, instead of, you have an underline there, so what I did instead, like, H of I and J, like, in parentheses, is that fine?
I don't care.
Then J.
Yeah. I don't care if you use MATLAB notation or LaTeX notation. Okay.
Supposed to be adding.
You have to do that.
It's in a comment though.
Any other questions?
So was that 26?
Yes.
So that whole thing is 26.
Well, okay.
We still have to use format rat.
Yeah, to get that formula, The other part of the problem is this, displaying the Hilbert matrix using
So
various
display,
formats, like these formats right here. So if you do format short, or format long, or format bank, those display the same matrix in different ways than my favorite format has. So the first part of the problem is displaying displaying the matrix in different formats. So that's for this part right here. And the second part is what I was talking about, getting a formula for the entries. So I want both pieces. Still got to time. Any other questions?
so did we just finish 26?
Unless there are any other questions about it, yes.
What is Hij in terms of I and J?
Do you have a formula? Okay. So, yes, that was a question I got earlier. So, what I'm looking for is an expression involving I and J. So that, okay, so I'll go back to the matrix. For example, the 2-2 entry, row 2, column 2, is 1/3. The 4-3 entry, row 4, column 3 is equal to 1/6. The answer I'm looking for is you think of it as a function of I and J, or an expression involving I and J, where if you plug in a row I in column J, will give you the entry in row I, column J of this matrix. So, like I said earlier, if you set I equal to 1, those are all the entries in the first row. So you want an expression that if I is equal to 1 would give you this when J equals 1, this when J equals 2, this when J is equal to 3, and so on. Because the idea is to look at the pattern in the entries. So if I do a correspondence between I and J, the row and column indices, and the I, J entry of the matrix. So row 1, column 1 gives you 1. Row 1, column 2 gives you 1/2.
So this is what format
Oh,
RAT
I
is
see.
trying to tell us.
Yes. Yeah, because if you look at the Hilbert matrix using any other format, it won't help you get this formula. But format RAT does, because they have these nice fractions here.
So this is what format RAT has been trying to tell us.
Yes. Okay. So extrapolating from these sample entries, notice, like, here's something to point out. The entry in row 1, column 3, so I equals 1, J equals 3, gives you 1/3. Here we have a 2-2 entry, I equals 2, J equals 2, also gives you 1/3. Notice that the diagonals, they go like from upper right to lower left. So this diagonal has 1/2, 1/2. This diagonal has 1/3, 1/3, 1/3. This diagonal down here is 1/7, 1/7, 1/7. So you want an expression involving I and J that would produce with the same diagonal and diagonal. Now, okay, I don't want to give away too much, but that's response to what I saw 2 years ago. Just show me evidence that you tried. Because of people's homework 2 years ago, I'm looking at, I see the other part of it, displaying the Hilbert matrix to formats, and then the discussion ends right there, and you're like, the whole class blew me off. So, yeah, not the whole class, but most. Okay. Other questions?
Number 18.
Okay. Okay. So you're writing a script. So this is when I say script, I mean it's an M file that has MATLAB commands in it. So you create two matrices. I don't really care what's used for M and N. But the point is the matrices should be the same size. So A and B have the same number of rows and columns. And then now the formula for the sum of two matrices is you're just adding corresponding entries. So Cij is equal to Aij plus Bij. So the idea is you write, in fact, this is the formula right here to compute the sum. So the idea is so this problem is for getting practice using for loops. And because you have to compute entries of the sum for all I and j, I covering all the rows and j covering all the columns, then that tells you how many for loops you need. So you need to use more than one for loop because you have more than one index to compute all of the entries. The next one, 19, is similar. Where you form two matrices of compatible sizes for matrix multiplication, and that too will use for loops. And in the this section in the appendix has a formula for matrix multiplication that you would implement. And for this problem, I'm fine with you just choosing an M and N, and it's not something that has to work in general. So you just,
I think I've chosen my M and N.
okay, so then you can, for instance, you could generate random matrices of the appropriate size or compose. Yes?
Is it okay if you generate both the matrices and like random matrices, but in the M and the dimensions as well?
Oh, random dimensions? Knock yourself
Like
out.
as long as it's like
Yeah.
works out according to their.
Whatever you got.
Yes.
N by N.
Yes, and I am and then random too.
But again, I like, you have
That'd
to
be
be,
the same thing as
you have to be careful with the interest.
that'd be the same thing as choosing whether you two or five. What did it mean?
E7.
Oh. Yeah, that's a section in the appendix. Yeah, that formula right there, that's the formula for the sum of two matrices.
Well, for M and N.
I think we're.
I know, we made it.
Should I pick an M and N?
No.
Okay.
Yes.
Yeah, so,
Like, no, I didn't see.
okay, so then you should generate a random matrix A of that size M by M,
Oh.
and also
Random matrix.
and random matrix.
A,
So great.
which is,
So I did the random, I didn't do in the end though. Why?
so a random matrix A, which is
M by N.
M by.
So
Any-
whenever it says n by n and it gives you, like it didn't give you like 3 by 2 or something, would that imply for us to find our own n rows?
Yes.
But if it would just said, creates two matrices A and B, would that just be, like, not that we would do that, but would that be like a vague A and a vague B matrix?
Yeah.
Like this.
M colon n is numbers between m and n. You need to use a random matrix. You can use the random function. Remember that from previous problems?
Oh, really, you don't hear?
A.
Something like this.
Oh.
A.
Wait.
I just put A. Rand and comma N.
Yes, yeah, like that. Yes, that. I did this sort of thing.
No, that's our special.
You did. Well, that's what to say that anyone who doesn't have questions is certainly welcome to leave. So,
Do you really want to say that?
um, point takers.
Yeah.
But I don't feel like I'm holding people here.
You're not holding us here.
Huh?
But what about B?
Same thing.
So B is also.
Yes, yes.
This is the little.
But are there any other questions?
I have. Yeah.
Right. Well, stop the recording.
Yeah.
Wait. That is what I wanted to do.